So, a little thought experiment. Hey, this gives us a chance to vote, I think. A mass, how about a rocket ship, is moved from the surface of a planet to a distance big R from the center. Which of the following is true about the work done? So I've given you count them, 5 equations to explain the work done. Which of those do we think is correct? Well, is A correct? Is work force times distance? I thought that's how it was defined. Why can't I use force times distance here? Because you're right. Why can't I? So?
It slowly starts to reduce.
It's the force is changing. This equation only works for a constant force, so I say no, no. And you know what? I think no, no, same idea there. In fact, I think the work would be right? Are we looking at the picture? Does it look like this rocket is in orbit, or is this rocket just going straight up? You know what? I'm going to assume that it starts and ends at rest. So we'll go to our simplest case that we're launching from like the North Pole or something like that. What's changing anything? Oh, so I can go mgh final minus mgh initial, right? Why not? What about gravity? Okay, the force is changing. Oh, so well, let's go take it one step further. I guess I have to use the cosmic, R final we use with a capital R. I have to use the cosmic potential energy equation. Hey, Manny, what do you want to point out to us? I know you have to understand what you're doing. So, what is the correct equation here? A, B, C, D, or E? D. Has to be. Is that okay? That would be how much work to lift something up, to fire a rocket straight up, but not put it in orbit. Explain your answer. We just did. There's our derivation right there. Then we talked about escaping from a planet's gravity. To escape from a planet's gravity means, in theory, to travel an infinite distance from the planet. Now, you guys argued with me last day, so practically it means to travel far enough away from the planet so that the pull of the gravity of that planet is basically zero, is negligible. And you don't need to go to infinity to do that. In fact, you don't need to go that far. To barely escape means to escape from a planet with no kinetic energy left at the end either. That you coast to a stop far enough away from the planet that it can't pull you back. That would be like you've run the numbers and you didn't waste any extra fuel. You did it just right. How much work would that take? Well, work would be okay. It would be negative big G, big M, little m over R final minus negative big G, big M, little m over R Earth. There's the change in potential. Manny, what do you want us to notice? Okay. Okay. If we actually get to infinity, what happens when we divide by infinity? Pause the video for 1 second. If you get out to infinity, who's in calculus? When you divide by infinity, when you take the limit as x approaches infinity, what did you get when you divided by infinity? What was 1 over infinity approaching? we can actually, if we actually do get to infinity, we can say that this eventually becomes 0 because it's relative to 0 at infinity. Really what we're saying is, oh, if the Earth isn't pulling on you, you're not going to fall. You have no potential energy because you're not falling. Is that okay? Change in kinetic. So we have plus KE final minus KE initial. Although we also said, Vikas, that we want to not be moving. So if you want the work equation, I guess it would be Manny minus minus, which is a plus, big G, big M, whatever mass you're moving, R Earth, minus however much kinetic energy you want it to start out with here on Earth. Oh, if we, well, there it is. Or if you want it to still be moving, big G, big M, little m over R Earth plus a half mv final squared minus a half mv initial squared. Pardon me? I added this to the notes over Christmas time. I can't remember what I was getting at here with this notion. I'm reading this and I'm going, I know we talked about escape velocity last day, but I didn't use work to derive it. I derived it using energy. So you know what, folks? After all that, I'm going to say nuke that for a second. I mean, it's cool, but I really want to handle the question on the next page. Because what's example 2 asking me to find? How much work? No. Speed. I think it's going to be speed, by the way. That's why I said how fast. Spencer, is there a change in height? Example 2, the next question.
Yeah.
Okay, can you stay there and find there? Because we're going to be on there for a while? Okay. Is there a change in height?
Yeah.
Is there going to be a change in speed?
Yeah.
Is there a yucky curvy path? Well, there's a changing force. This is a job for conservation of energy, not work. I'm going to go like this. Kiowa, underline barely escapes. What I mean by barely escapes is I want you to finish out at infinity going how fast? At rest. I want you to coast to a stop right when you get there. Is that okay? So if I want you to be at rest, what do I want your final speed to be? What do I want your final kinetic energy to be then? Whose phone? Came from over there. Nick's looking a little nervous. Wasn't you? So that's 0. Kohei's looking a little nervous. Guys, if no one answers it, it'll beep again. Keep an ear out. Don't let anybody put their hands in their pockets surreptitiously and try and turn their phone off. Just watch. I'm going to keep teaching. Keep an ear out.
It's right there. Check the notes.
Kiowa, you're okay with why I said that's 0? Okay, because it barely escapes. And now we're heading out away from Earth's gravity. If there's no gravity pulling you down, you can't fall. If you can't fall, how much potential energy do you have? So I can also go, the right-hand side of this equation is 0, which is kind of strange because you're saying, what, all of our energy adds to 0? It's because we've defined 0 at infinity. It'll still work because I'll get this. A half mv initial squared plus negative big G, big M, little m over R initial equals 0. How could I make this equation look a little prettier? Even before that, how can I make this equation look a lot prettier? I'm not going to cancel the masses yet.
Or not yet.
Move what over?
The potential energy.
So if I go like this, and say, I guess this is really what we're saying. It turns out all of your kinetic energy that you fire at the beginning is going to end up being how much potential energy you need to leave the planet. Which, that makes sense to me. I don't know what I was trying to get at with this work thing. Now I agree. Yay, yay. And yeah, now let's get the V by itself. In fact, we did this last day. We said escape velocity was equal to 2 big G, big M over R initial square root. Okay. I'm not going to bother solving this. We did solve this last day. I think it was 11,100 and 11,200. We can crunch the numbers, but I'm just going to pause here. Escape velocity is cool. Have I showed it to you? Yeah. There's going to be a couple of questions in your homework, but I need to make a little note. There's just so many things I'm throwing at you. I'm not going to put an escape velocity question on the test. It's cool enough, and you've heard the term, that I don't mind showing you where it comes from. Okay, and I'm pretty sure there's a question or two in the homework on it. There was last day, if nothing else. I like example 3, I like example 3, I like example 3. Ladies and gentlemen, I present to you the longest question of the course. Okay. Kiowa, what's the last thing they're asking me to find? To put it in? That's important because the work lifting and the work to put it in orbit, two different things. So what are they asking me to find? How much work to put it in orbit? To do that, I'm going to have to find all of the first things. So here's what I'm going to do. I'm only going to answer part 6, the last thing. And on the test, by the way, I'm going to give you the preamble. Rocket, I'll tell you the mass, blasts off from Earth or the moon, enters into an orbit. I'll tell you what the orbital radius is or the orbital period. And then I'll say how much work. Okay, so let's start with the last question. What does it want me to find? How much? Oh, so I can go, so if you want to, you can just kind of do this. Why can't I go force times distance? Yeah. Change in potential. Change in kinetic. Okay. I don't try and find both of these at once, but this is where we're going to cleverly use ditto marks and backspacing and all that on our calculators. Kiowa, what do you want to find first? Change in potential or change in kinetic? I don't care which. Change in kinetic? Okay. I'm going to change colors because I can. So change in kinetic. Kiowa, what's change in anything? Give him a hint, Alex. Final minus initial? Yeah, which is hard to say. I always say finus minus, it's tough, it's a tongue twister for some reason. Anyways, final minus initial. So change, by the way, this is why both in Physics 11 and in Physics 12, Mr. Kamosi and I emphasize this. Later on, we're going to be looking, for example, at change in voltage. It's going to be final minus initial. We're going to look at change in flux. It's going to be final flux minus initial flux. We're going to be looking at change. Whenever you see that delta, just think, oh, I'll find the final one, I'll find the initial one, and I'll subtract it. And Kiowa, although Josh has pointed out this is technically wrong, we're going to go simplest case. We're going to assume we're starting out at rest, even though technically, since we're on the Earth and the Earth is spinning, we do have some kinetic energy. It's from next door upstairs. Okay. Kiowa, what's kinetic energy, the equation been since Physics 11? Ke equals a half. Yep. Which V? Look up. Orb. Orbital speed. Did they tell me the orbital speed? Oh. Hey, wait a minute. I can find it. Gravity is what's pulling me in a circle. We've calculated orbital speed before. Big G, big M, little m over r squared equals m. Which circular acceleration equation do I want to use? Oh, the one with this, the speed in it, right? One of the r's cancels. Both little m's cancel. How would I get the v by itself? Square root. Wait. Kiowa, can you read that? What's that right there? Just read it to me. V what?
V squared.
Say it again. V what?
V squared.
What's in this equation here? V what? You know, instead of getting the v by its, instead of square rooting, why don't I just replace the v squared with gm over r? Isn't that a little cleaner? Little shortcut, not a huge shortcut, sorry, but a bit of a short. You could actually crunch the numbers and plug it in, and use your answer button, you'll be fine. But for what it's worth, hey, turns out I already got the v squared by itself. Why don't I plug that over? That's going to give me this. The change in kinetic is going to be 0.5 m big G big M over r. Don't write this down, but for what it's worth, isn't that actually just half the potential energy? Because wasn't potential energy big G, big M, little m over R? Oh, but positive. Okay, fine. That's just an interesting mathematical thing that pops out of here. You know what I'm going to do, because I want to be clever? I'm just going to go and tuck that there, because I have a feeling that big G and that big M and that little m, I might be retyping them later, so maybe I can reuse them on my calculator over and over and over and over and over. Let's find out. So first of all, let's find the change in kinetic energy. The change in KE, I left you guys a whole page. Yeah, good. It's going to be a half 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. What did the satellite weigh? 12,500, a rocket. Kilograms. This R is R orb, right? It's the final. This number here, is it an altitude or is it a radius? It says from the, so radius. But what are my units here? Okay, let's make a little note up here. Can you multiply that by 1,000? What do you get? How about 2.55 times 10 to the 1, 2, 3, 4, 5, 6, 7? R equals 2.55 times 10 to the 7th. Oh, how about R orb? Because R Earth, I don't want to get it confused accidentally, right? They're both R's. So down here is going to be 2.55 times 10 to the 7th. Alrighty. 0.5 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 12,500 divided by 2.55 times 10 to the 7th. I don't think I'm missing anything. No, I think I'll be good. No, if I use my scientific notation button, it'll actually do the brackets intuitive, like they're built in, they're baked into the... No, because my calculator will treat that as one number. If I physically typed a times and a 10 to the power of, then I would need brackets. But scientific notation, my calculator knows, oh, put this in a bracket automatically. It's going to be that. Is it in the 10 to the 10th range? That I've told you that's 10 to the 10th, 10 to the 11th, you're smiling. 10 to the 9th, if you're in a pretty low orbit. 9.7761 times 10 to the 10th. That's how many joules of energy, Kiowa, that we need to have to keep it in orbit. That's how much it's going to take to get it to the right speed. What else do I need to find? Not just the change in kinetic. Ugh. Okay, Kev. What's changing anything?
Final mass.
So it's going to be negative big G, big M, little m over R final, which I guess is R orbit, minus negative big G, big M, little m over R Earth. Right? Hey, Manny. Say what? Okay. Let's plug in numbers. The change in potential is going to be negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 12,500, all over 2.55 times 10 to the 7th. Run out of room. Oh, no. Duick says he's okay with you going ditto mark times ditto mark times ditto mark, dividing by, hey, what's that called, Kyle? It's called ditto mark. Our Earth, 6.38 times 10 to the 6th. Whew. Hey, Dale, I've typed a lot of this already. In fact, I think if I just backspace and if I delete the 0.5 times and replace it with a negative, don't I actually have the whole first term already? Big G, yes. Big M, yes. Little m, yes. Hey, our orb, winner, winner. You know what the final potential energy is? Negative 1.9552 times 10 to the 11th. (1552) plus. And then if I want to find the initial, I backspace. I change the minus sign to a plus sign. And I think I just change R to 6.38 times 10 to the 6th. That was way less typing. And I get positive 7.8147, no, how about 7.8148? 7.8148. 7.8148 times 10 to the, forgot to look, 11th. This is the longest question of the year if you've got a crappy calculator and you're having to rewrite and retype all of this. If you're taking some shortcuts, it's not too hideous. And hey, it's rocket science. I kind of like this question. Oh, I do like this question. You're gonna be asked a question like this on your test. I'm going to give you an orbital radius. I'm going to say, hey, how much work to keep it in orbit? Final answer is going to be that plus negative 1.9552 times 10 to the 11th. And I get 5.8596 times 10, 5.8596 times 10 to the 11th. 5.89, what did I say? 8596. Kiowa, did you help us find the change in kinetic? Say yes. Kevin, did you help us find the change in potential?
Yes.
Well, what's work? It's the change in potential plus the change in kinetic. I'm going to add up the two boxes. And yeah, this is a lot of work. Every pun intended that time. Work is going to be 5.8596 times 10 to the 11th plus 9.7761 times 10 to the 10th. Thankfully, I got this number already stored, plus 9.7761 times 10 to the 10th. And holy schmoly, 6.84 times 10 to the 11th joules. Now, that fuel there only accounts for the rocket. If you now add a payload, got another mass. I think I've told you, but it bears repeating. This is why it's about $10,000 per pound to put something into low Earth orbit. And it varies. If you want to put it higher up, like where the GPS satellites are, you're forking out more money. It's a little pricey. Example 4 says this. Use the expression for orbit speed, which was the square root of big G, big M over R. Prove that. Okay. Well, remember this. PE equals negative big G, big M, little m over. That's how much potential energy you have in orbit. Is that okay? Well, KE, Kiowa, is a half what? Kinetic energy? Yep. Yep. Which V? This would be KE in orbit, would be a half mv orbit squared, which would be a half. What's V orbit? The square root of this. What would V squared? What would V squared be? So you know what? Over here, let's write V orbit squared ends up being just big G, big M over R. Is that okay? So if I plug that in to here, I get or if I write it, I get little m times big G times big M over R. If I write that a little bit differently, Spencer, I get a half big G, big M, little m over R orb. Or this would be potential energy. That was the equation, but negative. What did I say I wanted us to prove? That kinetic energy is half of the potential energy. Oh, half of the magnitude, which really means, says ignore the negative sign. Turns out, now, I'm showing it to you, Alex, because it's nerdy. I've never really had to pull this out of my back pocket. I've used it occasionally as a shortcut. If a question asked, for example, how much kinetic energy there was in orbit, and I've just figured out how much potential there was, I know it's divide by 2, chuck the negative, and that's the answer. It's not enough of a shortcut that I've committed it to memory. Because I could also go, gravity is what's pulling me in a circle, and I could find V, and then it's a half mv squared. Oh, also it turns out the total orbit, and total energy, I'm going to call that TE. Hey, Max, if you've got $6, and Vikas has $8, what do you total? The word total, what does it mean mathematically? What mathematical operation does total mean? Add. Oh, so I think total energy is going to be potential energy plus kinetic energy. Is that reasonable? But we're cosmic. It's going to be negative big G, big M, little m over R orb plus a half big G, big M, little m over R orb. Hey, aren't these actually like terms? Is there a big G in everything? Is there a big M in everything? Is there a big little m in everything? Is there R orb in everything? Nothing else? Those are like terms. This is exactly like the following equation. Negative x plus a half x. What would negative 1x plus 0.5x be? That's what that is. Jason, it said, prove that the total energy is half the potential energy. Oh, yeah. Potential energy with a 0.5 in front of it. Okay, that's kind of cool. Oh, and part 3 says, prove that the total energy, see it, is the opposite of the kinetic energy. Oh yeah, they're the same thing, but that's negative, that's positive. We've already done that. Already did prove it. That's Mitchell under the kind of nerdly cool, but you can survive without phase. Just, it's nice to know, I kind of like, oh, the universe is pretty structured and organized, and I always love it when stuff kind of can be combined and written shorter and cleaner, and yay! So all we're going to do now is summarize the different situations. We're going to generate the equations and then quit. So here's the first situation. A rocket at rest, I'd probably underline the word at rest, blasts off from rest and rises to a maximum height h, or a maximum distance big R. Write equations to calculate the work done. Work? Well, work is going to be the change in potential. Mitchell, what's changing anything? Okay, so this is really going to end up being negative big G, big M, little m over R. Big R is R final from the picture, yes? Minus negative big G, big M, little m over R Earth. There's the change in potential. What's change in kinetic, Mitchell? What's change in anything? So change in kinetic is going to be a half m v final squared minus a half m v initial squared. This is going to be where we're going to start every work equation. Now, in this situation, are any of these zero? VI? What else? Mitchell, what does it say that we should assume here? Oh, what's VI? What's VF? What's my change in kinetic energy? So I could cancel it. You know what? Here's the equation. For this situation here, work is going to be negative big G, big M, little m over R plus big G, big M, little m over little r Earth. That's how much work it takes to lift something up. Have I memorized that equation? No, I know that work equals the change in potential plus the change in kinetic, and then I derive it. What else can we do? So, I wrote here, note, this is how much work to lift something in space or to shoot a rocket straight up. This will not keep it in a stable orbit. Why not? An orbit needs what kind of energy? Okay. What does B want me to find? What does B want me to find? Sorry, what? Height. Does it want me to find how much work? No. Is there a change in height, Manny? Is there a change in speed? Is there a yucky changing force? conservation of energy, but cosmic. I'm going to start out like this. Is my initial speed 0? Nope. Is my final speed 0? Yep. This is going to end up being a half mv initial squared plus negative big G big M little m over r Earth, because that's our initial. And that's going to equal negative big G big M little m all over our final. Yay! What does this question want me to find? Height. Height does not show up yet. What do I need to find in order to figure out the height? From what I have here, what do I need to find in order to figure out the height? R final. In fact, folks, let's go like this. If you want to, you can go. So at the very bottom, you can say this. Height is going to be R final minus R Earth. How would I get the RF by itself? I gotta be honest, here I wouldn't anymore. It's too complicated. To solve this, I would crunch this whole thing and get a number. Get the answer for that. That looks terrible. I would get an answer for this. That equals negative big G big M over R final. And once you have an answer for that big mess, you now have one fraction equals one fraction. Stuff moves diagonally. I would solve it that way. I would not try and get the RF by itself on the first line. It's yucky. It's yucky. What else? A rocket moving at speed v at liftoff. Oh, so initial velocity is not 0. Initial speed is not 0. Barely escapes. Oh, Kiowa, we said that that was code for final speed was 0, right? Coast to a stop. You gonna make it? Sneeze, sneeze. Tissues over there if you need them. I got the good ones. What kind of an equation does it want me to write, Trav? Write a. Now, what if they hadn't said that? What if they just said find V? Well, they didn't say how much work, so I would still start out with conservation of energy, because there is a change in height, there is a change in speed, there is a yucky, curvy, changing force. Okay? I would go like this. Nothing new there. You okay, Raj? Mitchell, you okay? You really look like you guys are focused on something, and I'm worried there's a phone hiding behind your binder foolishly that you're looking at. You're not, are you? Okay, thank you. You guys just looked like you were staring at something there for a second. What's V final? And if we get out to infinity, what's my final potential? 0. You know what? This is that equation where we ended up going a half mv initial squared plus negative big G big M little m over R initial equals 0. We then plussed it over. We then canceled the... You know what? This was the equation for escape velocity, which I think was 2 big G big M over R square root. Wasn't that what it was? I think that's what I get if I get the, right? M cancels, plus it over, times by 2 square root. Turn the page. 2 more and I'm shutting up. Whew. Clay, what's E want me to find? Okay, you guys with me? Because you've been yakking away for a bit there. What does it want me to find? Okay. Clay, looking at E without Spencer helping you, are we launching the rocket straight up and having it fall back down, or are we putting it into orbit? I'm going to ask you the same question. I'm just going to phrase it differently. Do we want the rocket to have some kinetic energy, or do we want the rocket to have no kinetic energy? In other words, my work equation is going to be where the change in kinetic is going to be a half mv orbit squared. How do I find v orbit? Gravity is what's pulling me around in a circle. Or maybe the question will tell you. Yay! Yesterday, the question told us each time. Yay! Raj, what's F asking me to find?
How fast it is.
So it's asking me to find a speed. Okay. Is it asking me to find how much work?
No.
Okay. Hey Raj, is there a change in height?
Yeah.
Is there a change in speed?
Yeah.
We're going to use conservation of energy, but since we're cosmic, we'll make sure we use the cosmic potential energy. We would go like this. Is my initial speed 0 in this question? Ah! Is my initial potential energy 0? Does it say we start out at infinity? So does it say we start out at infinity? Ah! Is my final kinetic energy 0? No, I think that's the V they want me to find. Is my final potential energy 0? Not in the cosmic equation, because 0 is out at infinity. Ugh. We're going to get this. A half mv initial squared plus negative big G, big M, little m over R initial. This time R initial is out in space. That equals a half mv final squared plus negative big G, big M, little m. Mr. Dweck? Yeah? How would you get the V by itself? I wouldn't. I would move everything over to that side, get an answer, get a number equals a half mv squared, and then I would get the v by itself times by 2 divided by m square root. But I would not try and do this one algebraic. Those are kind of the mixings and matchings and how I can, well. And we saw the how to fly the spaceship to the space station last day, yes? So homework, finish the stuff up from last day, but also number 3. Number 5. Yeah, 5 is a chunk. Seven. $15. I'm skipping a bunch. Technically, you can now do every question on the ultimate review. Tuesdays, I'm just gonna show you a few examples. In particular, we'll look at roller coasters and roller coaster loops and how that works. Okay? I don't wanna give you cool videos today. I wanted to give you a bunch of time. I was hoping to give you 40 minutes, 30 minutes. Some of you I know have other plans for basketball and things this weekend, so gives you a chance to take a big thwack out of the homework and get as much done as